So here I am just going to discuss the sensitivity analysis when there is a change in the objective function. Okay, that means here we are considering what? We are considering some changes we made in the objective function only, provided under the assumption the optimal solution is still feasible as the feasible region remains unaltered. That means the nature of the solution remains the same. The optimal solution remains the same. Only what you are doing, you are altering the cost constants. Okay, the ck you are altering by ck plus del k. Okay, so under that circumstance, if the optimal solution remain as it is, what we have calculated or we have already calculated, then what is the range of this del k up to which this remains still the optimal solution, and still obviously if you are considering it to be the optimal solution, then obviously this is feasible also. Okay. So what we are considering ki let ck be changed to ck plus del k. Okay. Now this ck, the cost coefficient here, may be either related to the basic variable or the non-basic variable. Okay, in the optimal solution. So let us first consider ki ck is associated with the non-basic variable xk. Okay. So what we are considering here ki let xb star be an optimal basic feasible solution to the LPP. This one. Here I am considering a maximization problem. Okay. So this is the maximization problem. XB star is an optimal basic for feasible solution. Suppose we have already calculated it. Okay. And let B be the optimal basis matrix. That means actually whenever you are following the simplex algorithm, you have ended up the sum, you have obtained the optimal solution. You have to concentrate on the last table. That is obviously the optimal table for this part of the analysis. Okay. So we are considering that only. So B be the optimal basis matrix in that case. Now let CB be the cost vector corresponding to XB star. For the optimal solution, as we have considered maximization problem, so obviously Zj minus Cj greater than equals to 0 for all j. Okay. Now what we are considering here, we del k with a change in Ck, then Cv is not changed, obviously because Cv is associated with what? Cv is associated with the xb star. Xb star is the optimal basic feasible solution. So, and we are considering here ki xk corresponding to the ck is not a basic variable. So this ck is not at all associated with this cb in the table. Okay, so that means there is no change in b. So zj minus cj remains, this will remain unchanged and non-negative for the basis vectors aj corresponding to the current optimal solution. Okay, one zk minus ck will change, where ck corresponds to the non-basic vector ak. Okay, that means what is actually happening, let us just concentrate, say suppose in this table. Okay, so here if you just see key, this is the optimal solution: x10, x40, x50, x25, x36 and x68. So out of 6 variables, you can just simply see key x1, x4 and x5 are the non-basic variables. So corresponding to them in the last table, this is the optimal table, the last table in the simplex algorithm where you have obtained the optimal solution. So here as you can see key this minus 130, that is this is a c2, c3, c6, these are related to the basic variables. So which are not related to basic variables? C1, c5 and c4. So corresponding to that, z1 minus c1, z5 minus c5 and z4 minus c4, all here, from here we can see the corresponding, this one say 1, this one and this one and this one. Okay, so these three are those which are corresponding to the non-basic part. Okay, so we are considering or rather focusing on these three, zk or zj minus cj. Okay, so that is what they are saying here. Okay, so those will be changing because you are considering a change of del k there. Okay, so that is what they are saying, one zk minus ck will change, where ck corresponds to the non-basic vector ak. I am considering here what? I am considering ki I am giving a change to the ck constant. Say suppose c1 constant there, again c4 constant, again c5 constant, like that. So c1 changing to c1 plus del 1, c4 changing to c4 plus del 4, c5 changing to c5 plus del 5, like that. Okay, so correspondingly those zj minus cj will be changing. Okay, so for all j, the inequality zj minus cj greater than equal to 0 will still hold, because you are not at all affecting the basic part of the solution. Okay, so if zk minus ck plus del k greater than equal to 0, then this remains the same as it is. Okay, so what is the constant imposed on this non-basic part? That this should be greater than equal to 0. So this should be greater than equal to 0 simplifies as del k less than equal to zk minus ck. one thing you just concentrate ki we are doing the sensitivity analysis after you have completed doing the sum, you have obtained the optimal table, so you have in your hand all this zk minus ck. So this right hand side here is known. What is unknown here? The unknown is a range of the sensitivity parameter, I must say here, the del k or the delta k, which is going to vary. So this is the unknown parameter. We are putting some constraint or we are putting some relation imposed over it in terms of the known variables or in terms of the known constants, I must say, that is the zk minus ck. So this is simplified in this one. Okay, so ultimately what we are getting, if you are considering ck as a associated cost constant with a non-basic variable xk, then for any of this, ck is a generic one, any of the non-basic variable you are considering, this ck, what is the constant or sensitivity parameter applied over it, you may change it by del k as long as del k is less than equal to zk minus ck. If you just restrict to this equation 1, then there will be no harm to the nature of the optimal solution, to the nature of the feasible region, up to the non-basic variable or the non-basic constant I have said till now. That is the case 1. Okay. Now is the case for the basic variable. Okay. So for the basic variable, let me just go here. When ck is associated with the basic variable xk. Okay. So ck, again we are considering the same thing. Ck is changed to ck plus del k. Let the optimal basis cost cb be changed to cb dashed. Obviously this will now happen because we are now considering the basic variables, and the basic variables are part of the optimal solution, non-zero part obviously. So if you are now changing the ck to ck plus del k, then definitely that will be affecting the cb in this table. Let me just refer to this table once again here. So suppose now I am changing this c1, and which one I said, c not c1 but c2, c3 and c6. So c2, c3 and c6, if you now change this, so suppose I am changing it plus del 2 plus del 3 plus del 4. So obviously what I am doing, I am changing here, correspondingly the change will be carried over to here. Okay, so ultimately you are considering the change in the or with reference to the optimal table. Okay, so what will happen in that case? If I change in the starting, that means here this is the one which is given z equal to cx. What I am doing, c2 plus del 2. Suppose I am considering c2 plus del 2. Then what will happen? If I start with your c2 plus del 2 from the very beginning, what will happen in the last part? The change will be reflected. The change will be shown in the cb part now. cb becomes now say cb dashed, where this will change, c2 will change because I have changed c2 at the very beginning. This change will be carried forward. Suppose you have you are doing the simplest algorithm for 5 steps. Suppose in the 5th step is the last optimal table. So starting from the first step up to the 5th step, this plus del 2 will be carried on. If plus del 2 is carried on throughout, so cb will no longer remain cb, it will become cb dash with some change here. I am considering only the c2 variable, so with some change here. Similarly, if you consider that you have changed the c3 variable also, so again there will be some change here. Correspondingly, if you consider that I have is c6 variable is also varied, you have also varied the c6 variable, then obviously this c6 here will also vary. Okay, so that is the thing they are referring to as cb dashed. Okay, so let us now go back. Okay, so cb dash, cb is changed to cb dash basis cost. Okay, Achha, cb being changed now, let us see the chain of changes which will now occur. cb is changed to cb dash, this is the first step. So as cb is changed to cb dash, what will happen? The zj minus cj will also be changed for all j corresponding to which the basis vectors are not in the optimal basis. Okay, for the vectors in the optimal basis, zj minus cj equal to 0. As they have, you are obtaining the optimal solution, we are referring to the optimal table. So for the optimal solution already reached, for those j, zj minus cj equal to 0, but those which are non-basic variables, for those zj minus cj greater than equal to 0, that will also be changed because there is a change here, because the basis cost is not changing, unlike the previous case where the basis cost was not changing. Here the basis cost is changing. Okay, so as a result of which this zj minus cj of the non-basic part will change, and the zj minus cj of the basic part remains as it is because it is already obtained 0 because of the optimality condition satisfied or reached. Okay. Now, corresponding to the non-basic variables part, that is the non-basic part of the optimal basis, let Zj be changed to Zj dashed, corresponding to the change in Ck. Okay. The solution obtained will remain optimal. Here maximal, obviously, because it is a maximization problem. So if Zj dash minus Cj greater than or equal to 0 for all j corresponding to the non-basis vectors, then only we can say key the optimal solution's nature, that the solution optimality is maintained. So I repeat again what I am doing throughout here. I am ultimately forced to consider the non-basic part of the solution of the non-basic part of the optimal solution. Consider Zj minus Cj corresponding to the non-basic optimal part. Okay. And put the constant Zj minus Cj greater than or equal to 0. Now Zj replaced by Zj dash because of the successive changes in Ck variable. So ultimately you have to see that Zj minus Zj dash minus Cj greater than or equal to 0 for all j corresponding to the non-basis vectors. Okay. Now let Cb be this, the cost basis. Okay. Cb dash now becomes this one. I am considering I am giving a change only in the Ck variable. So suppose as I gave with reference to the table, so C2 variable is changed to C2 plus del 2. Okay. So if that is the case, so suppose Ck plus del k is the change. So you can write it as it is. Okay. Like this. Obviously this notation is clear to you. Okay. Now Ik is the obviously unit vector corresponding to the kth component as non-zero. Okay. Achha, now we know कि this is already we have an idea from the LPP theory कि CB B inverse AJ is ZJ and B inverse AJ is YJ. Okay. So now what is happening? ZJ is changing to ZJ dashed due to the change in C from CB to CB dashed. So this we are writing as a whole. But what is CB dash? CB dash is this thing. So you just write it and break it because of the linearity factor. It is linear, so we can just simply multiply and break it. So as a result of which, what you are getting? CB B inverse AJ here plus del K B inverse AJ. So now you see CB B inverse AJ is what? This is nothing but ZJ. So you have written ZJ, and this is what? This is del k ykj with ik as we have considered the unit vector. So ultimately zj dash is taking this expression zj, that is the older initial zj, and del k into ykj. What is del k? Del k is the change or the variation which we have made in the ck cost constant. Okay. Thus the condition now let us impose is zj dash minus cj greater than or equal to 0 because of the non-basic optimal solution part. So zj dash is this expression minus cj greater than or equal to 0. So altogether if you put, you get this thing for all j not in the optimal basis. Obviously, as I already said, for if you consider j from the optimal basis, suppose if I consider the c1 c2 variable in the this table, if you consider the c2 variable in this table, it is already a part of the basic solution. Okay. So there will be z2 minus c2 is already 0 here. Z2 minus C2 0, Z3 minus C3 0, Z6 minus C6 0. There is nothing change you can just do here. If I want to maintain the optimality condition, if this is my the last optimal table, okay. So what I can vary? I can vary this one, I can vary this one, I can vary this one. So these all correspond to the non-basic part of the optimal solution. So that is what they are saying. You have to focus everything on this non-basic optimal part. Okay. So if I now put this constraint here, z dash minus cj greater than or equal to 0, then ultimately again this reduces to this one. Okay. And here if you can see again, as I said before, this part is known to you because already we have obtained the optimal table. Ykj is known to you, only del k is the unknown. That is the parameter range we have to sort out from here. Now there is two possibilities. There are two possibilities here depending on the nature or the signature of ikj. If it is positive, then obviously this reduces to this one. Okay. As it remains, as it is positive, simply you can take it downside. Okay. But if it is negative, this signature, this sign will change. So this is the thing. So for ykj greater than 0, this is the constant over del k, and ykj less than 0, this is the constant over del k. What are your ykj's? These are everything corresponding to the non-basic optimal part. Okay. So combining these two restrictions, ultimately you are getting this thing. So for our purpose, for sensitivity analysis, we have to use this one. We have to calculate this within this minimum over this argument. So this you have to calculate. and this we have to calculate. So this is the range of the del k. Okay, for all j for which aj is not in the basis. Not in the basis means the non-basic part. Okay, if del k lies in the range as given earlier, then the solution remains optimal. If del k falls outside this range, then at least one zj minus cj will be negative and the solution will no longer remain optimal. So what is they saying? Obviously, how did we obtain this range? We obtain this range under the assumption that the optimal solution remains as it is, that is remains optimal. So if I bind to or use that assumption, then this is the range. If you use, or if you suppose I am considering the C2 variable, I am giving a change. So suppose del 2 is coming between 0.2 to 0.4. If I am now giving a change which is greater than this 0.2 or 0.4, then what will happen? Obviously this theory part will break. This theory part will break means the optimality of the condition will not be maintained, and obviously then you are hampering the solution. That is not a part of the sensitivity analysis. Okay, so we have to restrict our change of the cost coefficient by this amount. Okay, so here we are getting some special derivations from here. You may just say here if no yk is greater than 0, okay, then obviously what you are getting, there is no lower bound of del k. Okay, because obviously del k you are getting ykj, if it is no greater than 0, then what you are getting here, this part is not coming, only this part is coming. Okay, in that case del k greater than equal to this part remains invalid or becomes invalid, so lower bound is not obtained. Similarly, ykj less than 0, if no ykj less than 0, then what will happen? Minimum of this will not be valid. So obviously del k's upper bound gets lost. Okay, there is no upper bound of del k in that case. Okay, so now let us do the specific example so as to get a clear idea of what we obtain in the theory. So what they are saying here, find the limits of variations of the costs C1, C2, C3 up to C5, sorry, up to C6 respectively for the linear programming problem whose optimal table is given below, so that the optimal solutions remain optimal. Okay, so this is the thing which you are getting here. So this is the last table which you have obtained. Okay, now as I said already, key x1 variable, x1 variable, and then x3, x2, x3 and x6 variable. Here we are getting x1, x4 and x5 variable to be 0, and x2, x3 and x6 variable to be the basic part of the solution. Okay, and z max, there is a maximization problem, is equals to 30. Okay, so we notice that x1, x4, x5 are non-basic variables. This is a very crucial point to note down, because based on this only this del k will be coming. Okay, so x1, x4, x5 are the non-basic variables in the optimal table. Hence the permissible limits of the variations of c1, c4, c5, which are del 1, del 4, del 5, are given by what? By the first part of the analysis. First part of the analysis means what? This part of the analysis, ck associated with the non-basic variable. Here x1, x4, x5. So c1, c4, c5, if changed by c1 plus del 1, c4 plus del 4, c5 plus del 5, del 1, del 4, del 5 are restricted by this and this part. So equation 1 is to be used there. So we segregate the non-basic part first, then we find out this as the limits del 1, this one. What we did, as I said already, key I am using the table, the optimal table. So z1 minus c1, right? So what is z1 minus c1? z1 minus c1 is 6 by 5. So del 1 is less than equal to 6 by 5. Del 4 less than z4 minus c4. z4 minus c4 is 4 by 5. So del 4 is less than equal to 4 by 5. And del 5 z less than equal to z5 minus c5. So it is 17 by 5. So you can simply follow what they are trying to say. So the three cost constants you may vary. If you want to keep the optimal solution as it is, that the variation del 1 should not be greater than 6 by 5, del 4 should not be greater than 4 by 5, and del 5 should not be greater than 17 by 5. Okay, if they are greater, then this optimality part is lost, and again you have to do the entire sum from the very beginning. Okay, now what we will do, we will just approach for finding out the cost coefficients associated with the basic part of the solution. So that means c2, c3 and c6, which are the cost corresponding to the basic variables x2, x3 and x6. So for this, which part of the theory to be used? Case 2 to be used. Okay, so case 2 to be used means this part, as I already said last key, this is the thing which will be used. Now this one, so again this part is known to us. This is also we will have an idea from the table. Everything is known, so this will impose a bound over this C2, C4 and sorry, del 2, del 4 and del 6 now. Okay, so let us now see how they are doing it. Simply just rapidly using the table, nothing else. Acha. So now let us consider key y2. Okay, because C2 corresponding to x2. First one I am just considering. So what is the del 2's limit? Via the theory, this is the del 2's limit. So how I am going to find out this one? Let us correspond to the column, second column, this one, right? Second column. This one. Acha, let me just see once more. Y2j. Okay, from the table Y2j, we are getting this one. Okay. Acha. From here, this one, sorry, not this one, my mistake. Along this we should move. Y2j means Y21, Y22, Y23, Y24, Y25, Y26. So Y2j is this row. Okay. So Y2j is this row. So this is, you can see which one we should collect. The Y2j corresponding to j as a non-basic part. So what are the non-basic part? X1, X5 and X6. So I should be just seeing over 2, 5 and then 4 by 5 and then 0, right? Let me just see once again. Not x6 but x5, x1, x4 and x5. Achha. Then y21, y24 and y25. Okay, I will consider first the whole thing, then our focus will be one on the non-basic part of the y2j's. So y21, y24 and y25, all of them are positive, no negative thing is here. Okay, so let us write it once. Y2j is this thing. Acha. Now we are to consider those y2j for which j corresponds to non-basis part. That means j equal to 1, 4, 5. That means y21, y24, y25, as I said. So this thing. Acha. So this is completed for the C2 part. We are just collecting. We have not till gone to the case of del 2's range. Okay, we are just first collecting and then ultimately we will go to the range of del 2, del 3 and del 6. Similarly for del 3, which row we should consider? Y3, third row. Achha. For the third row, let us see. Y3, 1, Y3, 4 and Y3, 5. See, the whole Y3j is the whole this thing. Now Y3, 1 is this one. Y3, 4 is this one. Y3, 5 is this one. Again, there is no negative part. So all this will be used when we try to find out the range over del 3. Okay. Now last one. What is the last one here? C6. Okay. That means I have to see the sixth row. Okay. So the sixth row, for the sixth row, this will be, this what they are doing, they are collecting the non-basic part only. Okay, so 1, 5, 3 by 10, 2 by 5. Similarly for the last one, C6, this one, what will happen? The non-basic part. So this one and this one and this 1 minus half and 10. 1 minus half and 10. Okay. So these are the three things we are collecting. Why we need this? We need this to put here because it's non-basic. Y2j's, Y3j's and Y4j's are to be used. Okay. Y2j's, Y3j and Y6j. Okay. So once I get all this thing, you now can simply just calculate on your own, and zj minus cj from there also you are getting, so z2 minus c2 by y2j. So here also you are getting the z2 minus c2 means this one. Okay. So let us see how we are getting it here. Okay. So no y2j, first of all, no y2j less than 0. So as I said, this part of the bound will not be coming. So only the max part of it will come. So for the max part, we are getting this one. Minus 6 by 5, minus 4 by 5, minus 17 by 5. Where from you are getting it? Here. Minus 6 by 5, minus 4 by 5, minus 17 by 5. So for the 1, 4 and 5, that means the non-basic part, as I said. So minus 6 by 5. Why this minus is coming here? Because of this minus. Okay. So Z1 minus C1, Z4 minus C4 and Z5 minus C5. And below we are putting Y21 That means z1 minus c1 by y21. Let us see z1 minus c1 by y21. z1 minus c1 is this thing and y21 is this thing, and minus in front of it. So minus 6 by 5 by 2 by 5. Let us see if they have just written it here. Yes, minus 6 by 5 by 2 by 5. Okay. Then the seconds for 4. So z4 minus c4. So z4 minus c4, this one. Okay. And what is the variable? Here for the fourth one, it will be y4j. Sorry, why not y4j? But here we are considering the y2 only, the y2j. Okay. So for the y2j, that means the second row we will be considering. For the second row considered here means here we are considering the 1 by 10. This one. Second row means I am just saying it wrongly. If I consider this the first row, then this is the second row. Actually, I am fixing the index corresponding to this one. Okay. So for that one, this is 1 by 10. 1 by 10, it is 4 by 5. So minus 4 by 5 by 1 by 10. So minus 4 by 5 by 1 by 10. And similarly, the last one, minus 17 by 5 by 4 by 5. So last one means here again, the fifth variable for the second row. So the fifth from the second row. This one. From the this is the z5 minus e5, and the y2 5 here is this one, this y2 5. So minus 4 by minus 17 by 5 by 4 by 5. So minus 17 by 5 by 4 by 5. So ultimately, if you just simplify it, you will get this thing. So del 2 obviously less than equal to infinity. That means it can be extended to anything up to positivity, and but it should be greater than equal to minus 3. Similarly, del 3 obtained like that. For that, what we have to consider again, z3 minus c3. Okay. So similarly, just as we calculated this and this, you have to just check on your own how they are doing it from the table. Okay. So once you do this, then del 6 and del 3, all these ranges are specified. And previously we have obtained the del i's for the other three i's. So it is 1, 4, and 5. So ultimately you are getting the bound of the variation of the parameters over for all the 6 cost coefficients. Okay. So this amount, if you just vary this and by within this amount, then the optimal solution will remain as it is, and there will be no change in the optimality condition or the feasibility condition. So this is the sensitivity analysis. Now there was another thing which is attached to it, how much sensitive is your solution to the change of these coefficients. Okay, how much sensitive means what? For that thing, let us just consider, or let us just analyze like this. Suppose we are changing the variables. So suppose I consider 3 variables, suppose. Okay, so let us just see, suppose I am considering just hold for a second. Okay. So suppose what we are doing here, so suppose for one variable, say x or rather c1, suppose you have obtained the range del 1 within say 0.2 to 0.4. Okay, again for another cost coefficient c2, you have obtained del 2 to be 0.5 to 0.9. Again I am considering, say suppose 3 are there, del 3 to be within minus 0.2 to plus 0.5. Okay, so as you may see, what are these ranges? As I said, if you give this amount of changes, then the optimality remains as it is. So if I now do not give this amount of changes, the optimality will be just damaged. Okay, so that means this is the variable range for which delta 1 change in the C1 variable will not affect your solution. Okay, outside, if I consider the whole real line, say this is my point 2, this is my point 4, this is my point 5, and this is my point 9, and along with this is my point minus point 2. So up to this one, if you give the delta 1 amount of change, there will be no change in your solution part, right? But other than that part, if I give any change of this C1 variable, then there will be change in the optimal solution. Okay, so this length of this range is smaller than this one or this one. So if I want to vary the optimality of the solution, then it is easier to change del 1. That means what I am saying, ki del 1 is more prone to affect your solution. Del 1 is more prone means C1 is more prone. Okay, so slight change beyond this range will change your optimal solution. But here del 2 is varying over a large range, 0.5 to 0.9. So this del 2 is lesser prone than del 1, okay, with respect to your solutions. Del 2 means C2 is less sensitive. In that case, C2 less sensitive than C1. Ultimately, you can see here for this one, this is much higher range compared to 0.2, 0.4, 0.5, 0.9. This is the largest range. So del 3 is having a variation or can be varied over a large range compared to this one and this one. So C3 is the least sensitive one. Your solution is least sensitive to C3's change and most sensitive to C1's change. So ultimately, what is the net thing you have to look into? Range of variation of delta K, and then minimum range implies corresponding cost coefficient, or rather I must say minimum range implies ki the solution sensitive or rather most sensitive to corresponding cost coefficient change, or rather corresponding cost coefficient. And maximum range implies solution least sensitive to corresponding cost coefficient, corresponding cost coefficient. Okay, so this is the thing. If we want to analyze the sensitivity, which one of the cost coefficient is most sensitive or which one is the least sensitive, then you have to find out these ranges. So ultimately the net thing depends on you solve the problem via the simplex algorithm, you create the tables, you obtain the optimal solution, thereby obtain the optimal table, use the optimal table according to the theory just discussed, so as to find out the ranges of variation of these cost coefficients. Okay, for the non-basic cost coefficients part and for the basic coefficient cost coefficient parts, and obviously the least of these ranges will give you the most sensitive part of the solution or most sensitive cost coefficient. The largest of this range will indicate the corresponding cost coefficient is the least sensitive to your solution. Okay, so in this last part here, what we obtained for the part del 2 greater than -3, del 3 greater than -8/3. So here the range is more than this one, because what we will get here, some 2 point something. Okay, so this range is greater than this one, and this range minus 6 by 5, so minus 0.6 by 5 means zero point 0.1 something. So again this one is more restricted than this one and this one. And let us see for the other three. Here the other three are corresponding to del 1 less than equal to 6 by 5, and it is unbounded on the other side, so it is the large range. Del 4 less than equal to 4 by 5, it is unbounded on the other side, so again this is large range. And del 5 less than equal to 17 by 5, again unbounded on the other side, so this is one is also a large range. So out of this del 1 up to del 6, which one is the minimum range coming? Minimum range coming for this one, this is the most restricted one. You can just see I am saying this one, but you rather check it on once you're on your own key whether I am saying the correct thing or not. If this is the thing, then your solution is most sensitive to the change of C6. Okay, it is most sensitive to the change of C6. Okay, I will rather suggest please just see once again key whether I said it correctly or not. Key this is the least C6 is the most sensitive to your solution, change of C6. Okay. So this is how we did for the maximization problem. The same thing you can just design for the minimization problem, but there you have to use the corresponding condition of zj minus cj, which we used to design it for the maximization problem. Okay. So simply you have to change the theory accordingly if you want to do it for the minimization problem, but the whole strategy remains as it is. Okay. So let us stop here.